All right, Stephen Farrington from Transcend Engineering, talking about low-cost soil moisture sensing using Wi-Fi channel state information.
Hello. It's great to have this mobile mic because I can pretend I'm Phil Donahue here and walk back and forth. Um, Probably about one third of the crowd knows who that is. I'm going to rip through these quickly. First, a quick introduction. How do I switch a slide? Actually, I just hit spacebar. Perfect. Um, Transcend Engineering, we're a little different animal than most people in the room. We're not like a mature manufacturer, and we're not a research agency with a government affiliation or anything. We're a small business, and we do R&D for hire, and we build an intellectual property portfolio that we license to other people. We work in these areas, and we work with people like you. So just a quick recap of why I'm here talking about soil moisture. We've done some work in the past. Scott might remember this, where we developed using TDR a method of continuous profiling, and using that technology as the basis for AI that I presented last year at this conference. We developed a method of just observing the soil moisture profile in high resolution to infer the root water uptake in specific crops and to infer the deep drainage to the water table or beyond the root zone. And in the process of that, we discovered we did not need the data density of the prisms, which is about every centimeter. And we could do it with any of the commercial probes that were available for multi-level. And so we calibrated this method for a bunch of those. We did a lot of work, like Leo was just presenting, in terms of characterizing the volume influence and the noise and the bias and the uncertainty, so that to train this stuff, which we did with 50,000 simulations of irrigation scenarios in every Surgo soil in which various crops are grown. We That was all driven by Hydrus. Anyway, we had characterized that because this box up here, where we understand the sensors, and we had to convert those theoretically perfect simulations into what the sensor would actually see in order to make this work. So anyway, the premise of this work is that we didn't like the cost of all the multi-level sensors. Our experience talking to a few growers indicated that they saw that as a barrier, and some distributors of soil moisture sensors saw it as a barrier outside the research world to actually use these in an orchard or a vineyard. And so we said we would attack that problem with some exciting new technology. I'm just going to move through these more quickly because I'm not going fast enough for my time limit. So our proposition is that dielectric permittivity is the property we're interested in. It also affects the transmission of radio frequency signals, as we know from TDR, although those are on a transmission line. It does it in open field too. And these modern Wi-Fi chips have come so far. For $3, you can get an ARM processor with a 5 gigahertz transceiver on it, and in the embedded silicone, it is collecting signal information constantly in order to support these multi-antenna systems you see on routers. They're modulating how much signal is going to each of those antennas and how much power and time delays in order to basically beam signals to your cell phone or your tablet or wherever you are in the field, and they're compensating for the multipath. So there's this whole rich set of information available about signal propagation from these things for $3 a chip. So we said, can we use that in this is an animated slide. Okay, so I've already talked about this. Cost is low, capability, usability are unprecedentedly high. All that information is exposed in the software interface on that ARM processor, right? So the idea here is, my radiated field went away. So this is not drawing correctly, but we have a transceiver chip radiating a field here, and some of that is going through the soil. So a lot of it's direct, and it's being picked up by another chip. And if we can sort through that rich set of data to figure out what the influence of dielectric of that field outside the probe is, then we might be able to build a low-cost sensor by putting pairs of these together in a dense vertical array. Right, so we got funded by NOAA to do a phase 1 SBIR. It's a Small Business Innovation Research Grant. And our approach for this proof of principle was to build these environment vessels which would basically drain pipe um, and make soil columns in them, and well, media columns, I'll say. Collect the channel state information, look at the, explore the data and see if we're seeing a correlation between the dielectric of the standards we're putting them in, to evaluate the connectivity effects, and then see if the performance that we could achieve will be comparable to what's available commercially for soil moisture sensors. Because if you can't do that, there's no point in pursuing this any further. And then also assess the production costs and see if our assumptions about what it would take to build one of these things, because they're actually end up being a little bit more complicated than we anticipated, would be make for a viable market entry. So this is our vessel design. I mentioned it's a drain pipe. Basically, we've got, we're simulating a probe body with a 1-inch diameter fiberglass tube. We got some 3D printed parts centralizing it in there. We have a 3D printed fixture that makes sure that the two transceivers are exactly the same geometry, exactly the same depth in the medium for every test we're doing. And then in the space in between, we put soil. We tried polyethylene beads. We tried lots of things. We tried a lot of just pure fluid standards. And this is the finished columns. And this is a picture of sort of the various fixtures. We worked with 4 different antenna designs. The 3 that come on some of these dev boards that have the chips on them. There's a modified F printed circuit board. There's this strange bent metal radiator, and then there's these chip antennas that you can get also. And the orientation of those, we found out, matters a lot, of course. And so our media standards we ended up settling on after a lot of attempts to try to drain these columns and provide a continuously changing environment so we could really fill in the dielectric range. Those all failed because we don't understand how to deal with capillary issues in draining columns, despite having help from experts in the field. But anyway, this is just to show we came up with these standards, and they're pretty well distributed over a reasonable range of soil moisture, as shown by these well accepted curves like top and Ledoux. First, looking at the CSI amplitude. So CSI, this channel state information, it contains, oh my God, the most important thing is 64 subcarrier bands of amplitude and phase information, centered around the transmission frequency. But it also, because these chips are smart and they're constantly adapting to the environment, they're changing their modulation scheme, they're changing their subcarrier bandwidth, they're changing all sorts of things. And in software, we had to kind of lock that all down and hobble them so that we could get consistent subcarrier band information on the amplitude and phase. And if you just look at this across the whole 64 bands, you can't see any discernible patterns with respect to, the medium that it was in. But if you kind of zoom in on different regions, you can see that you can pick up this frequency-dependent fading as a function of dielectric, which is exactly what those chips are designed to compensate for with that information, is frequency-dependent fading. And so we worked with the, well, we actually ended up working with 48 bands. I'm going to move on with that. So we tried to see if that data was self-organized with some self-organizing maps and some k-means clustering and stuff like that. We didn't see any patterns emerge, so we jumped to a random forest to see if we could do a classification of which medium they were in. You might sound like not a well-conditioned problem because we have so much data and so few standards, but we did a lot of cross-validation and limited the inputs to this. And these are just some of the confusion matrices as to which one it was in. I think we performed, in the worst performing antenna and shielding configuration, we got 93% accuracy, and several of them produced, 100%, to round it to the nearest 0.1%. Then we did a regression analysis with a simple neural network design. It's just one hidden layer, one layer of inputs. There's a schematic of it with only 5 nodes shown, but we had 96 nodes because we carried 48 subcarrier bands with, we converted amplitude to power, and we carried the phase. And I just realized I can see what I'm presenting up here. We trained it using stochastic gradient descent. What I neglected to put on this slide is that we were doing 80-20 training testing splits with n-folds cross-validation. And then with a specific antenna design that we found worked the best, which was actually our own proprietary antenna, we did 20-fold cross-validation because of the way we had to cluster the data from switching between actually 2 antennas. Here's results that kind of show what the what the histogram of errors were. We were predicting log of parent dielectric, and then there's a box and whisker kind of showing us the spread in each of the standards. But the phase one findings, I already mentioned, making these smoothly draining columns was very challenging. So we hope in phase two, if we get funded, to do a better job of that. Shielding between transceivers is necessary to keep down the direct communications. We experimented with a bunch of different shielding designs and found what worked best. At low power, our columns were not enough volume, right? So we saw environmental effects from outside. So then we kept the columns, but we carefully controlled that because this was just a proof of principle. But when we move into phase two, we'll be making a much larger confining area for these. And we got our best results from not only a proprietary antenna design, but when we multiplex between two antennas on each transceiver so that we have that spatial diversity, because that adds another dimension to the problem. That helps you separate what's going direct path from what's going or helps the machine learning separate that from what's going through the medium. For a soil at 20% volumetric water content, our mean square error corresponds to about 2% volumetric water content. And that's in line with the published accuracy of a lot of commercial sensors. So we felt we should go forward and apply for the phase two. I just want to acknowledge NOAA for the funding through their technology partnerships office. And a lot of people were involved in this. Rocky and Robert and Max did the electrical design and the embedded programming. Max did the design of all that 3D printed parts. Dave Wessner and M did the lab experiments. You see a lot of Farringtons here. It's kind of like Campbell Scientific. And Keith and Kevin did the machine learning analysis of the data. So, how am I doing for time? We have questions? Okay. I can run to them, Nathan, and get my steps in. Paul.
Did you try a configuration where you just had one rod transmitting and one receiving at different depths to? Well, like, because you're picking up Wi-Fi signal from within the same this.
Yeah, so all of these were between pairs only, where we programmed one to be the router and the other one to be a client on it. And in the final product, did I have a picture of the conception of the final product in there? In the final product, we would have. I think I skipped a slide or didn't get to it. Oh, there we go. See on the right here. Sorry, I somehow I blew by this. This is sort of the cost comparison and sort of the data density per cost. This would be a string of 10 of these, and we built up a notional design and a bill of materials, and we talked to a contract manufacturer about what it would take to kind of build that, and that's how we arrived at this cost estimate for what we could achieve. I don't know if I answered that question adequately. But and then software would switch which one was paired with which, and then ultimately, you could do interesting things like not just pair adjacent ones, but pair farther apart ones, and see how much penetration you can get, and create like a tomographic data set that you could solve for to try to resolve finer layering or horizontal variation in your environment.